All right, so yeah, welcome to the crypto seminar. Today we have Pedro, who's going to talk about batch OT with optimal rate. So Pedro, the floor is yours. Take it away.
Okay, thank you so much for inviting me. And today I'm going to talk about OT with optimal rate. And this is a joint work with Zvika Brakerski, Nico Dotling, and Siangpo. And please feel free to interrupt and ask questions if you want. Okay, so let's start with the definition of oblivious transfer. So OT is a primitive between a sender on the left side with input bits x0 and x1, and the receiver with the input bit b. In the end, the receiver should get x beam. So in terms of security, we want that the receiver learns nothing about the other message, x1 minus b, and that the sender learns nothing about the receiver's bit b. And it's well known that the minimal number of rounds to perform OT in the semi-honest setting is 2. Okay, before we start, I just want to set some terminology. So when I refer to OT, I mean batch OT, which are n independent copies of bit OT. The upload rate is the ratio between the receiver's input B and the receiver's message. And the download rate is the ratio between the receiver's output and the sender's message. And we say that
yeah, I think Elena has a question. So yeah.
What is B? That's the question.
So B is a vector of bits, which corresponds to the receiver's input. Okay, and we say that the OT has overall rate 1 if both the upload rate and the download rate are close to 1. Okay, and it's very easy to see that the information theoretical lower bound is 2n. Okay, so we need at least 2n bits to perform n independent copies of OT. Okay, so n bits from.
I don't understand the definition. What is upload rate and what is download rate? I don't understand these variables.
Okay, so in a 2-round protocol, we have a message from the receiver to the sender, and the message from the sender to the receiver. Okay. The upload rate is the size of the receiver's input over the size of the receiver's message. Okay. And the download rate is the size of the receiver's output over the size of the sender's message. Okay, so it's the ratio of information contained in each message of the protocol.
So just to clarify, like you send for all n copies of the OT, you send all messages at the same time, like n messages, kind of.
So I want to batch them. Okay, I'm performing n independent copies of OT at the same time. Okay.
So B is the input in R n copies, or it's the input in 1 copy?
No. MR is the receiver's message in this batch OT protocol. Is the size of the receiver's message in this batch OT protocol.
But B is Rn copies. B is the input in Rn copies. So why is this copy?
What? Sorry.
B is a vector.
Yeah.
Yeah.
So MR is the size of the receiver's message. Isn't that size n?
Yeah, that's what we want, right?
So I guess B is like a vector of bits that
Exactly.
the receiver wants to choose, and but
Exactly.
MR is the message of the receiver in the OT protocol.
Exactly.
Right.
Exactly.
And X in the same way, XP1, XPN are like the actual senders, data that they want to exchange in the OT, but MS is the message of the sender in the OT protocol, right?
Exactly. Exactly.
So why is it called upload rate? Like, shouldn't the receiver be downloading?
So you send one bit B and you get back XB. So upload in the sense that receiver sends something and download in the sense that receiver receives something.
Yes. Okay. Are we clear? Because this is actually important.
Yeah, I think it's fine. Yeah.
Okay. So if we think of the insecure protocol,
Sorry,
the receiver needs to send n bits, which corresponds to each input for each copy of the OT, and the sender needs to send. It selects the right bit, right, and sends this bit to the receiver for each copy, right? So we need at least n bits from the receiver to the sender, and n bits from the sender to the receiver. Okay.
One more, yeah. Sorry, one more quick question. So the rate is a vector.
It's the left.
The rate. Okay, so the notation is not very good. So the B is a vector, and the rate, the upload rate, is the size of this vector over the size. Okay, over the size of the receiver's message in the OT protocol. Okay.
I see. Thanks.
Okay, and likewise, okay, so this is the size of this over the size of this. Okay. Perfect. Okay. So can we build OT with overall rate 1? That's the question. And the answer is yes, if we use rate 1 fully homomorphic encryption. But the drawback is that we can only do that from LWE. So what we ask in this work is whether we can build OT with overall rate 1 from assumptions other than LWE.
Can I just ask, like, what's the problem with LWE itself? It's like it's post-quantum, right? So.
Yeah, but it's a natural question in cryptography to ask which assumptions do you need to build something.
Yeah. Okay.
And it turns out that the answer is a bit more complicated than in the LWE setting. Okay. So what we show in this work is that we can build OT with overall rate 1, which is secure against semi-honest adversaries. Okay, and here security, sender security holds under one of these assumptions, so LWE, DTH, or QR, and receiver security holds under one of these assumptions plus LPM.
What is QR?
QR is the quadratic residuosity assumption.
Okay.
Okay.
So a quick question. So if we assume LWE, then the solution is just use rate 1 FHE.
That's true. That's true. That's true. I mean, it was not the goal of this work, but we also get it from LWE. But that's true. With LWE, you can do it just using fully homomorphic encryption. Okay. As an additional result, we show how to build function private linear homomorphic encryption from DDH, and where operations are done over Z2. Okay, and with ciphertext rate 1, but we'll get to that later.
I'm sorry, another question. So if we if we assume LWE and use FHE, then we can we go back to the previous slide?
Yes.
Do we still need Lpm assumption for receiver security?
No, if you use FHE, you just need LWE. So it was actually not a goal of this work to achieve, OT from LWE, but and LPN, but we also get it.
Okay, another question, like, are your protocol, like, if we want to implement something, are these the most competitive in terms of concrete performance, or should we look at some other thing for practical implementation?
Oh, in terms of, I mean, it should be efficient as, I mean, we don't have practical results. Okay, so we did not implement it, but we just use black box techniques. So we should be, it should be efficient. So there's a problem for the rate to kick in. For the amortization to kick in, you need to run many executions. Okay. So if you want to just perform, let's say, 2 OTs, then probably there are better implementations.
Sorry, I have another question. So you say rate 1. I mean, I guess this like your rate converges to 1 as n goes to infinity, right?
Exactly.
Yeah. How fast is the convergence? Do you know? Or is it vanishing?
Let me think. Well, it needs to be something polynomial in the security parameter, but I'm not sure. It depends. We did not compute that.
Okay, that's fine. Thanks.
All right. Okay. So yeah, so a lot of recent works have studied this problem of the communication complexity of OT, and the best known results were these works based on silent OT extensions. So silent OT extensions essentially allows us, the receiver and the sender, to get random OT correlations using very little communication. But then if you want to de-randomize these correlations, the parties need to incur in a communication proportional to 3n. Okay. And recall that the optimal rate is 2n. So a couple of other works also achieved download rate 1, but very poor receiver rate. And as we've seen, we can actually do it from FHE, but just based on LWE. Okay. All right. So how do we achieve our result?
So for the silent OT, I couldn't interpret what you said. Can you go back to the previous slide? When you say base 3n for n bits, does that mean the rate is 3 or the rate is actually 3n?
So the rate is okay. So it's not rate, right? It's communication. Communication 3n bits for n bit OTs.
That's 1/3 rate.
Okay, because you need to de-randomize these random correlations.
So the rate is 3?
No.
So for the receiver it's 1. The rate is 1, but so this is the receiver's rate, and the sender's rate is 1/2, right?
Oh, right. Okay. I see.
Okay.
That's right.
Yeah. Sorry about the typos.
No worries.
Okay, so we start by considering the naive protocol of OT from Elgamal, okay? And then we improved the download rate by using known techniques by Dotling et al. Then to reduce the receiver's rate, we perform a re-encryption step, okay, to get upload rate 1. And this is where we actually use the Lpm assumption. But then we sort of introduced 2 new problems. The first one has to do with the Lpm errors. And for that, we built a new primitive that we call co-PIR. And the second problem is that if we want to instantiate this from DDH, we need an Elgamal encryption scheme, which is function private over Z2. Okay, so to solve this problem, we show how to emulate small subgroups in ZP. Okay, but we'll get into each of these steps in more detail. So let's start with the simple OT from Elgamal. The receiver will first compute, will first create a public key, an Elgamal public key, right, which is composed by G and H, which is G to the X, and the ciphertext encrypting the bit B. Okay, the ciphertext is composed by G to the R and H to the R times the B. The receiver sends the public key and the ciphertext to the sender. And now the sender will homomorphically evaluate the OT function. So the OT function is this function f of x, which computes m1 minus m0 times x plus m0. So first note that this is a linear function. And second, if x is 0, then the output is m0. And if x is 1, then the output is m1. Okay? So the sender will evaluate this function over the ciphertext, and the resulting ciphertext C1 prime, C2 prime will encrypt the message MB. So now the receiver uses the secret key X to decrypt the ciphertext and obtain MB. So sender security follows from the function privacy of the scheme, you know, given by this randomizing term R star, and receiver security follows from the in-CPA security of Elgamal. In terms of communication, the sender sends 2 group elements for a single OT execution, and the receiver sends 4 group elements. So we're very far away from optimal rate. Okay. So any question?
Oh, fine.
So here, if we want to achieve rate 1, how many group elements should it be?
Okay, so a group element is of size lambda bits, right? Each group element has lambda bits. Okay, so we're still very far. I mean, here we have a rate of 1 over 2 lambda, right? So let's see how we can improve this, okay? All right. To get download rate 1, so to reduce the sender's message, we're going to use a ciphertext compression technique, which was presented in this work of Dotling et al. For the batch Elgamal encryption scheme. Okay, so recall that the batch in the batch Elgamal scheme, the public key is composed by G and the components HI, which are equal to G to the XI. Now, an uncompressed ciphertext is essentially an Elgamal ciphertext. Okay, for each of these components, and importantly, we need to use the same randomness in each of these terms. Okay, so we use the same randomness R in each of these terms. Now we know that there's an algorithm that transforms each of these terms into single bits. Okay, this is known from the work of Dotling et al. So the way we do this, I mean, I can show you very quickly how to do this. So the encryptor knows that there are two possible values for C1, right? So either C1 is encrypting 0, in which case C1 is equal to H1 to the R, or C1 is encrypting 1, which means that C1 is H1 to the R times G. Okay? So if we draw here ZP, or the group, sorry, the group, we know that C1 is here, and we just need to, H1 to the R is here, H1 to the R times G is right next to it in terms of multiplications by G. So if both parties, both the encryptor and the decryptor, can agree on a breaking point, the encryptor can compute the distance between the ciphertext and this breaking point by multiplications of G. Okay, so he multiplies C1 by G until he hits the breakpoint. And now we know that since they H1 to the R and H1 to the R times G only differ by one multiplication of G, we know that one of these values, the distance of one of these values to the breakpoint is even, while the other is odd. Okay, so the encryptor just needs to signal which one he's sending to the decryptor. Okay, and the breakpoints are defined by a PRF key. That's why we also need this term in the compressed ciphertext. All right. So it's very easy to see that the rate of this ciphertext is L over L plus 2 lambda, right? Where you know, lambda bits for this group element and lambda bits for the PRF key, and this goes to 1 as L goes bigger, right?
So the betas are in the clear. Is it like this break point is hidden, or what? They cannot all be in the clear.
Oh, what? Sorry.
Are the betas in the clear? Like the beta is just one bit.
The breakpoints are in the clear. Yes, everybody knows the breakpoints.
But then the beta is also in the clear. So then the ciphertext, why is it secret?
What? Sorry.
Is it because it's due to the R thing is secret? Like I'm just asking. It's okay to make both the breakpoint and other beta in the clear.
I'm sorry. I don't.
Is there a problem? I guess is there a problem with like having the betas and the breakpoints all being known?
No. No, because this is a post-processing operation. Okay.
I see. I see. It's only a function of the original ciphertext.
Of the ciphertext, exactly. Okay. Perfect. So how can we use this to obtain a download rate 10T? The receiver is now creating a batch Elgamal public key and ciphertext CTI, which encrypt vectors which are equal to 0 everywhere except for the ith position where.
How do you decrypt it? Like, is decryption very expensive? Like in the previous slide.
What? Sorry.
The previous slide is decryption very expensive. Like, how long does it take to? How do you decrypt it efficiently?
No, sure. I mean, we compressed at the cost of computation. Yes. But it's still polynomial. If you set the parameters of the PRF correctly, you can make this process polynomial time.
So this
Okay.
K is not, this breakpoint is not uniformly a random chosen.
No, but it doesn't have to be. It doesn't have to be. It doesn't have to be uniform. It just have to define a set of breakpoints. Okay, this was something used in also in homomorphic secret sharing. This is where this idea comes from.
Can you just remind me what the PRF is doing there? Sorry.
So the PRF is defining these breakpoints. So they need to agree on these breakpoints.
But this breakpoint is sufficiently close to those ciphertexts for decryption to be.
Yes, they need to be close, but you can ensure that with with overwhelming probability if you set the parameters correctly. Okay, if you for a proper choice of parameters, this runs in polynomial time. Okay. All right, so the receiver sends a public key of the batch Elgamal and ciphertext CTI, which encrypt the vector which is 0 everywhere except for the ith position, which is equal to BI. Okay. Now the sender will homomorphically compute the OT function on each of these ciphertext CTI and obtain the ciphertext CTI prime, which are equal to 0 everywhere except for the ith position, and on which they encrypt the receiver's output. Now, if we sum all of these ciphertexts, we get an encryption of a vector which has the output of the receiver in each of these in each of the components, right? Now we can use the compression algorithm from the previous slide and get a ciphertext CT tilde, which encrypts the receiver's output with rate 1. Okay, so now the receiver can decrypt and obtain the output. So in terms of the sender's message, the size of the sender's message, we are happy because since CT tilde is rate 1, then the sender's message is also rate 1. But in terms of receiver's rate, the receiver needs to encrypt each of these CTIs encrypts a long vector, right? So the receiver's rate is actually worse than before. Okay. So we need a way to reduce the receiver's rate. So our main idea to reduce the receiver's rate is to perform a re-encryption step. And for that, we need an encryption scheme which has rate 1 and for which decryption is a linear function. And it turns out that using the learning parity with noise assumption is a natural approach because LPM almost fulfills these requirements. Okay, so first recall that the Lpm assumption states that for a random matrix A, a random vector S, and a sparse error vector E, the distribution of S times A plus E is indistinguishable from a uniform vector.
How large is T there? Like the Hamming weight?
We just need it to be sublinear in M. Okay. So also notice that the matrix A, if we set the parameters correctly, A can be very expanding. Okay. So the output of A is much larger than S. Okay.
So here, A and S are randomly drawn from the. So here A and S are random and E is a fixed vector with ending with T.
It's not fixed. It's sampled. It's sampled uniformly from the from the set of vectors with Hamming weight T.
Oh, so E is also like randomly sampled.
Yes, yes, but with Hamming weight T. Okay.
Okay.
All right. Perfect. So we flip some of the positions. Okay. So if Alice and both share the secret S, we can very easily build a symmetric encryption scheme from this by setting a ciphertext of the message M to be S times A plus E plus the message. Okay, so an Lpm sample plus the message. And decryption, we just remove the S times A part from the ciphertext and get a noisy version of the message. Okay, so we get M prime, which is M, where some positions are flipped. All right. So now to reduce the receiver's rate, we're going to do the following. The receiver will create, again, a batch Elgamal public key, but now it will encrypt the secret S under the Elgamal encryption scheme. It will also send a vector C, which corresponds to an Lpm sample together with the with its input B. Okay. So now the sender will homomorphically decrypt the Lpm sample on the exponent and then apply the OT function as before. Okay. So notice that the sender will get an encrypted will get an encryption of the receiver's output where some of the positions are flipped. Okay, so this is equal to the OT function f of b plus this term e. This symbol corresponds to the multiplication coordinate wise, e times m1 minus m0. Right? Some of these positions have this extra error term. So we need a way to deal with these error positions. And that's what I'm going to show now. And then there's another, we'll get into this later. Okay, to deal with the errors, we present a new primitive that we call co-PIR. And in a co-PIR, we have a receiver with input a set of indices S and the sender. And after interacting, the sender obtains a string Y of size M, and the receiver will also get a string such that the receiver string coincides with Y for the positions not in S. Okay, so if the receiver gets Y bar, then YI is equal to YI bar for I not in S. In terms of security, so essentially this string has some holes on it. Okay, so in terms of security, we require that the positions YI are pseudo-random to the receiver. And we also require that the sender learns nothing about the receiver's input. Okay. In terms of communication, we want that the communication scales only with the size of the sender's input, and not with them. Okay. So we call it co-PIR because in a PIR the receiver gets the receiver would get these positions, but here he gets everything except for these positions. Any question?
Yeah, I just find the notation very confusing because like the different fonts of S mean different things.
I guess there's a
Oh,
sender.
that's yeah, that's true. So this is set, and this is
Yeah.
sender. Okay.
Yeah, I guess in the third step as well, right? Yeah.
S has no information about set, right?
Yeah, exactly. Okay, perfect. Yeah, now it's much more clear. Thanks.
Okay. So we can build this primitive from what?
I don't think there's anything. Yeah. Go on.
Okay, sorry. Okay. So we can build this primitive from puncturable pseudorandom functions and PIR. And actually, this work of Boyle et al. Built something very similar from punctual PRFs from based on GGM together with OT. Okay, so how can we use this to correct the errors? Well, both the receiver and the sender will run the co-PIR. Will run a co-PIR where the receiver's input corresponds to the support of the error vector. Okay. Support of the error vector.
Sorry, support of the error means the
Means the
set.
positions where the error is equal to 1.
Okay,
Okay.
thanks.
Now the sender will use this string that he obtained from the co-PIR to mask the output of the receiver inside the encryption scheme. Okay. For the positions, for the positions where there's no error, then the receiver, the receiver string from the co-PIR will come inside with Y, and thus the receiver can remove this mask from the output. Okay, but we still need to correct these positions where the error is. And for that, they will use an additional PIR where the receiver's input is, again, the support of the error vector, and which will allow the sender to essentially send to the receiver this value for the positions where the error, for the error positions, right? And since YI by the security of the co-PIR, since YI is pseudo-random to the receiver, then this value is pseudo-random to the receiver, and thus it has no information about M1 and M0, but will allow the receiver to correct the errors. Since both the PIR and the co-PIR have communication sublinear in the number of OTs that we're performing, then the total communication of the protocol will then the rate of the final protocol will tend to 1. Okay. All right. So there's one missing piece.
So how many rounds do you need for this co-PIR?
Okay. Yes, that's a good question. So all of this, the co-PIR, the PIR, and the OT protocol can be performed in parallel. So we only need 2 rounds.
Thank you.
Okay, so the last missing piece is that Elgamal doesn't support operations over Z2. So to perform the linear LPM decryption, D minus S times A, this is a function. This is an operation modulo 2. But ZP, but Elgamal only supports operations over ZP. Okay. So this might actually leak some information about the sender's input. If we were on the QR setting, so in the QR setting, ciphertexts are of the form -1 to the M times G to the R, right? And the message is encoded in a subgroup of order 2. So operations, if we apply an operation over M, then this operation will be over Z2. And this problem doesn't appear in the QR setting. So what we're going to try to do is to emulate a subgroup of order 2 inside ZP, just like in the QR setting. So as a first idea, if this is ZP, here we have 0, and here we have P over 2, which doesn't exist, right? As a first idea, we're going to encode 0 as 0 and 1 as an element close to P over 2. Let's say a ceiling of P over 2. Okay? But there's a problem, which is, the errors will accumulate in a predictable way. Okay, so if we sum 2 bits, then the result will be the sum of the 2 bits modulo 2 plus an extra term. And this extra term, if P and B prime are equal to 1, then this is equal to 0. But this will be equal to 1, whereas if both bits are equal to 0, then this will be equal to 0. So we can distinguish the cases where both bits are equal to 1 or both bits are equal to 0. And this breaks the function privacy that we need. So to solve this problem, we're going to use a technique from the lattice cryptography world. We're going to use something called randomized encodings, which was introduced by Pickard. And the randomized encoding is essentially, a randomized encoding of a real number R is essentially a discrete Gaussian centered on R. So it's very easy to see that a randomized encoding of R plus a randomized encoding of R prime is equal to a randomized encoding of R plus R prime with a slightly larger Gaussian parameter.
Just a quick question about the notation. So bracket R subscript sigma is an encoding of a real number R with,
which is and this is essentially a discrete Gaussian sampling, discrete Gaussian sample centered on R with parameter sigma. Okay.
So is it an integer or a real number?
It's an integer, right? It's a discrete
This
Gaussian.
integer, but R is
it's
not.
R plus integer, I guess.
Oh, I see.
R is what? R is
R is a
also
real number.
Okay. All right. So what we're going to do is we're going to encode the bit B as a randomized encoding of B times P over 2. So essentially, if this is ZP again, and this is 0, we're going to encode 0 as an element close to 0 by a discrete Gaussian, and 1 as an element close to P over 2. So the idea is that the errors will accumulate when we do operations, but they will accumulate in a non-predictable way. Okay.
So this encoding is an integer, right?
Yes, it's an integer.
I see.
It's an integer. Okay, so if we want to evaluate the function f over x1 and x2, we're actually homomorphically computing another function f prime, which always adds an error independently, of x1 being 0 or 1. So we always add an error. Okay, and it's very easy to see that if we apply f prime to b1 and b2, so this is b2, we get something which is statistically close to a randomized encoding of f b1 b2 times p over 2. And this is actually simulatable because given the output of the function, we can create a ciphertext that is indistinguishable from an evaluated ciphertext. And that's how we achieve function privacy for Elgamal for Z2 operations. Okay, so just to conclude, as an additional result, we obtain very similar results in the Oblivious Linear Evaluation setting, for certain rings. And as open problems, recall that we only consider semi-honest subversion. So malicious security is a natural question, a natural follow-up question. And another follow-up question is whether we can remove LPN and get a scheme just from DDH or QR. We could also remove one of these assumptions, but this actually seems harder than removing LPN. Okay, that's all. Thanks.
Any questions?
Yeah, I have a question about the malicious setting. So could you go back to the previous slide? Yeah. So your scheme, both receiver and sender are semi-honest.
Yes.
Okay. If I use FHE, then can we achieve like one side is malicious?
So first, in the malicious setting, you need a CRS.
Yes.
But I guess you can achieve receiver's malicious, receiver's malicious security, using something similar as PVW, right? As Picard by Quintanathan and Waters. If you create your public key depending on the CRS, then I guess you can achieve malicious receiver. Yeah.
Only malicious receiver, but the sender still be.
So the sender, I mean, so there's actually a subtle issue here, right? Which is if you want UC malicious security for the sender, you cannot consider rate 1 protocol, right? Because in UC security, you need to extract the sender's input. But if you have a rate 1 protocol, then the sender's input is not well defined, information theoretically.
Oh, I see.
Any more questions? Right, so yeah, if not, then let's thank Pedro again.
Yeah, thank you.